I've got here a wooden block on a horizontal surface. I've put paper down just to create a more uniform surface. Wood on wood often tends to be really quite tricky for friction because you get like sticky spots on the wood. String goes over a pulley. I've done my best to get the string horizontal, and on this end there is a mass. If I set this mass into motion, swinging through oscillations of a small amplitude, then nothing happens. If I set this into motion through starting at a much bigger angle, you can see that there's a period in each cycle when the block moves. Try that again. The question is how big do we need to make this angle in order to make the block slide in these kind of jerky movements, and why does it slide in a jerky movement rather than a smooth movement? Okay, the diagram shows the initial position with the string at an angle that I'm going to call alpha to the vertical, and the position at some stage in the motion at an angle that I'll call theta. Alpha is the release angle, which is fixed. Theta obviously varies during the motion. The two forces we need to consider are the tension in the string and the weight force. Resolving towards the centre of the circle here, we have T minus mg cos theta, which will be our resultant force, and that will be equal to the mass times the acceleration, which we will take as v squared over r. So T will be equal to mv squared over r plus mg cos theta. Now we need to consider the energy. The kinetic energy here will be equal to the potential energy lost. So the kinetic energy is a half mv squared, and the potential energy lost will be mg times r cos theta minus r cos alpha. This term is the difference in height between the two. So from this we can say that v squared equals 2g r cos theta minus cos alpha. Combining these two expressions, substituting for v squared, noting that the r's will cancel out, gives t equals 2mg cos theta minus cos alpha plus mg cos theta, which will simplify to t equals 3mg cos theta minus 2mg cos alpha. I will now consider the forces on the block. If the block slides, then the tension force must be greater than the friction. We're obviously talking about a case where friction will take its maximum value, so we can say that T must be greater than mu r, and T must be greater than mu mg, where capital M is the mass of the block. This is a graph that shows how the tension would vary for angles between minus 90 and 90. It's basically the cos graph translated downwards because this quantity here would be fixed. I could also add onto this graph a horizontal line at a height of mu capital MG. So for angles in this range, the tension in the string will exceed the maximum friction available and the block will slide. But when the tension drops, as can be seen here and here, then the friction will be sufficient to stop the block sliding, as the maximum friction available will be greater than the tension. If the value of alpha is small, as would be the case for a small angle, this term becomes larger, so the cos curve will be pulled down further. And in this case, a horizontal line at a height of mu mg would always be above the curve. This explains why, when the angle of release is small, there is no movement. For the block to slide, the tension must be greater than mu mg. Using our expression for the tension, 3 mg cos theta minus 2 mg cos alpha, we arrive at this inequality. We can cancel the g's, and I can rearrange that to show that cos alpha must be less than 3m cos theta minus mu m all divided by 2m. Now in my experiment, m is equal to 0.521 kilograms, little m is equal to 0.12. I'll determine the value of mu to be approximately 0.25. Now if I substitute those values, it will give us like a limiting value for cos alpha, where the tension only exceeds mu mg at the lowest point. So what I'm going to do is I'm going to assume that because we can see the block moving, that at a particular angle, a particular value of theta, the block starts to move. So I'm going to take theta as 10 degrees. If I substitute those values, I end up with cos alpha must be less than 0.934, so that alpha must be greater than 21 degrees for the block to slide. I'm now going to try and find the smallest angle of release for which there is some movement. I've clamped a piece of wood here so I can know where I've released the mass from. So here we go with a fairly small angle, and you can see that there's no movement at all. So I'll move this away so that we increase the angle of release. Still no movement. A little bit further. At this angle there's a very small amount of movement. Using a protractor I can estimate this angle at around about 20 degrees.